Hey everyone, welcome to this class 16b, where Wout and I, Jeroen, will tell you more about the Maxwell relations and where we will show you how you can use these relations to derive other interesting and useful equations in thermodynamics, including the Clausius-Clapeyron equation. Now let's start off with a recap of the previous class 16a, where we introduced you to the four different thermodynamic energies or thermodynamic potentials, if you will, and where we introduced things like the Helmholtz energy and the Gibbs energy. Um, this is an overview of the various energies expressed in their full form or in the differential form. And we also show that we could derive partial derivatives and show that these are equal to thermodynamic properties like the temperature, the pressure, the specific volume, and the entropy. So in fact, these partial derivatives that we can obtain from the total differentials uh, give us definitions of thermodynamic state variables. And all these four thermodynamic energies are, of course, state functions, and their differentials are total differentials. And these equations are also what are called fundamental equations of state. Now, at the end of class 16a, we had just seen that there are in total 8 important properties in thermodynamics. And we had seen that we are always taking partial derivatives that involve 3 variables. So you can have in total 512 different partial derivatives, and we had only seen a few of them. So there are still about 500 partial derivatives left, and some of them contain very useful expressions. Um, for example, the ones that have a variation of the entropy on board. And if you can relate that to something that is measurable in terms of pressure or temperature, then this gives you a very nice tool to find these inherently difficult terms that involve variations of the entropy, because entropy cannot be measured directly. Now, the question is, of course, still how to derive all these different partial derivatives that you could think of. And you can do this in various ways, as we will see during this class and the coming class. But in this class, we will look specifically at what is called the Maxwell relations. The Maxwell relations are named after James Clerk Maxwell, one of the great minds of the 19th century. His name is often mentioned, and he's considered to be on par with people like Einstein and Newton, and he has done many things. He was fascinated by light and colors. He was the maker of the first color picture. And the Maxwell relations that we will talk about today should not be confused with the Maxwell equations, which deal with a different discipline of physics because it deals with electromagnetism and electromagnetic waves. And if you ever get close to a physics department, you might see students walking around flaunting their knowledge of physics, showing these Maxwell equations on a t-shirt. And well, if you realize that your classmate is wearing this t-shirt and you was planning on wearing the same t-shirt, you can always try to trump him by wearing a t-shirt with the Maxwell equations in integral form. And let's dive directly into it, into these Maxwell relations and how does it work. What I'm going to show here is more like a hand waving explanation. It will provide you a trick to evaluate the Maxwell relations relatively easily. And this is how it goes. Suppose we have an internal energy of the variables S and V. Then we can write down the total differential like we usually do. And then we can compare this total differential with the first Gibbs equation. And like we had seen before, it turns out that this partial derivative here is equal to t, and this partial derivative here is equal to minus p. All right, now let's keep this in mind. And let's take a look here at the first term of the left-hand side of this equation, I'm going to take a partial derivative of t with respect to the other variable. So not the variable in the first term, but the variable of the second term, something like this. And I'm going to do this for a constant entropy, like this. All right. And I can do the same thing for the second term. I can take the partial derivative of p, or actually minus p, with respect to the other variable, s, like this. And I will do this for a constant specific volume, like this. Now, the Maxwell relation is basically the equality between these two terms that we just so hand-wavingly derived. And what you see here, this partial derivative dt dv for constant entropy being equal to minus dp ds for constant specific volume, this is the first Maxwell relation. And in total, we will see 4 Maxwell relations during this course. Now, of course, we owe you a more decent mathematical proof of what we just did, so let's take a look at that. Now, from class 15b, you may remember that we talked about combined or mixed derivatives, which are of this form here. It's basically taking a derivative or partial derivative with respect to one variable, and then you take the result and you take another partial derivative of that with respect to another variable. And this here will show up later on this slide. Now we've also seen this total differential here of a function z of variables x and y. I don't think we need to explain this, but what we do want to do is rewrite this such that this partial derivative here becomes equal to m, and this partial derivative here becomes equal to n. Now, if we would apply the trick that we just learned about, we would expect that if we take the partial derivative of m with respect to y for fixed x, that would be equal then to the partial derivative of n with respect to x for fixed y, like we show here. So this is what we want to prove, but this is actually correct. Now, let's do that, and we'll do that the following way. Let's take partial derivatives of m to y for fixed x and another partial derivative of n to x. So then we get these combined partial derivatives. And if you want, you can stop the movie here and take a closer look for yourself to see if you will follow this whole derivation. But what's basically written here is that this partial derivative of m with respect to y is basically this mixed partial derivative here, d squared z with respect to, or d squared z dy dx. You can do a similar thing for n, and that results into another mixed partial derivative, d squared z dx dy. So the only difference between these two guys is that the ordering of the x and the y's is inverted. Now, there is something that we perhaps should have told you when we talked about total differentials and their specific properties and requirements. Because one requirement for a total differential or an exact differential is that these are functions that are at least doubly differentiable. And if they are, then they automatically fulfill the criteria for the so-called Clausius-Schwarz theorem, which says that if you have a mixed partial derivative like this, it's equal to this mixed partial derivative. And this basically says that the ordering of the dy dx or the dx dy, the ordering doesn't really matter. It doesn't matter which order you take these different partial derivatives. It's equal. And in that case, you arrive at the expression that we were trying to prove. So this is basically our proof. And if you're interested, you can always feel free to look up Wikipedia about this Clausius-Schwarz theorem, but it's by no means part of the subject matter that you need to know for the exam. Now, 2 slides ago, we already found the first Maxwell relation between this dt dv and dp ds. We derived that using our little trick that we proved on the previous slide. And we can also do a similar thing, not for the internal energy, but we can do it for the enthalpy, which we write as a function of the entropy and the pressure. So we find this total differential. We can compare that with the second Gibbs equation to find that the temperature is actually equal to this partial derivative and the specific volume is equal to this partial derivative. So far, so good. Now we can apply again the same trick as before. And we have to apply that to this total differential form here, which I'm repeating here. So what we will do is we will take the partial derivative of T with respect to P for fixed entropy S, that's this term, and that's equal then to the partial derivative of V with respect to S for fixed P. And this here is our second Maxwell relation. Now here on this slide is the same derivation of, again, the second Maxwell equation, but this time now showing all the steps that we saw before spread out over different slides. All the steps are now shown here on one slide. If you think that the previous stuff was not entirely clear to you, you might stop the video and take a look until you get it and then continue the lecture. Now, like I mentioned earlier on, there are actually 4 Maxwell relations. And there are indeed 2 more Maxwell relations because we have the Helmholtz energy and the Gibbs energy. And for these, we can also write down total differentials. And we can apply the same trick. And that leads to the 3rd Maxwell relation and the 4th Maxwell relation. And these relations are extremely valuable in thermodynamics because they enable the determination of entropy changes in terms of things that can be measured easily. So this ds dv is equal to dp dt, and this is stuff we can easily measure. And that was one of the reasons why we started this whole endeavor. And there's actually much more to the Maxwell relations. They also have a connection with phase diagrams. And in the following movie, Wout will show you how what this connection is and how the Maxwell relations can be used to derive the so-called Clapeyron equation. And then later, during the video lecture, we will see how we can even derive the Clausius-Clapeyron equation from that. And Clapeyron and Clausius, these are another 2 of the great minds that of the 19th century, people that are really the founding fathers of the modern thermodynamics that you're still learning about in 2020.
Dear students, welcome to another video. This video is about the Clapeyron equation and phase diagrams. And actually we're going to construct a pressure, temperature, phase diagram. And we're going to construct this since pressure and temperature are often the most easy to measure variables in thermodynamics. So you can just measure it by a thermometer or a pressure gauge to measure temperature and pressure, and that's very easily actually. And it is especially interesting for us as engineers, since most chemical processes or thermodynamic processes aren't actually visible. So you have to determine the phase depending on pressure and temperature. So that's why we're going to derive equations, the Clapeyron equation, which is able to describe the change of pressure and temperature depending on phase. So let's start. At first, of course, there are three phases, and it depends on pressure and temperature. And well, just by common sense, we can already determine in what phase a substance will be under a certain pressure and temperature. So if pressures are really high, really high, and temperatures are reasonably low, my phase is usually a solid. So high pressure, low temperature, the phase will be a solid. For high temperature, low pressure, we can of course estimate that we will have a vapor or a gas. Vapor. And for a relatively high temperature but a high pressure as well, we will have liquids. So the liquid comes over here. Of course, as we know, these phases are separated by saturation lines. And I'm just giving an indication of these saturation lines because the Clapeyron equation will actually help us to determine the exact behavior of these saturation lines. So I'm going to draw them schematically now by, so let's assume we've got a solid over here, and it behaves something like this until, well, let's say here. So, and we're going to make these lines solid, but not now. We need to know the equations first, describing this line. So over here, this will be the line of phase transition, and over here as well. Oh. A little bit more. So these are the saturation lines. Saturation lines. So, and we're actually very interested in the behavior of these saturation lines. So we're going to draw them at the end of this lecture, a video. So, to be able to draw these, we need the equations of Helmholtz plus Maxwell, and these are derived before, so I'm not going to derive them, but it will be delta pressure, or the partial derivative of pressure to temperature for constant volume is equal to the derivative of entropy, the partial derivative of entropy with respect to specific volume for a fixed temperature. And this is our basic equation which we are going to use to determine the behavior of these lines. And well, this one thing we first need to notice when we're talking about phase changes, because when we're talking about phase changes, we know, so let's write it down here, phase change. When we're having a phase change, we know that the temperature is the saturation temperature, and the pressure is the saturation pressure. And well, what we actually know for pretty sure, that the saturation pressure at which the phase change occurs, so the saturation pressure, we know pretty sure that this only depends on the saturation temperature. So it's a function of the saturation temperature only. So from knowing this, we know that dP, or the partial derivative of the pressure for a specific volume, becomes a total derivative. And that means that I can write it like this: dP dt at, and remember, only at saturation conditions, so at one of these lines. And this is really important to know before we start doing our mathematics. Well, actually now it's very useful to look at our old faithful TS diagram. And I'm sure you can draw this by head right now. And we're going to actually make use of this, because when you look into this diagram, you will notice that, well, this is one of the isobaric lines. So the pressure is constant. And during phase transformation, which actually occurs over here, you can see that over here we've got the liquid entropy, and over here we have the vapor entropy, so the saturation line of vapor. Here we have the critical point, and we know that over here the temperature is the saturation temperature. So we know that this temperature over here is constant as well. And now we're actually going to use this diagram to make an estimation of this derivative using this. Because when we look at the saturation line, you can say that dP, not color, you can say that dP over dt at this saturation line is equal to the difference in entropy divided by the difference in specific volume. Well, and for entropy this will be the vapor entropy minus the liquid entropy divided by the volume of the vapor minus the volume of the liquid. The entropy liquid vapor divided by V liquid vapor, or, and that's even more useful in our diagram, as delta S over delta V. Okay, and now, since I'm really interested in the behavior of these lines, I'm going to draw the dP, dt lines to make an estimation of these lines. And, well, first I'm going to start with the phase transition from a liquid to a vapor. So let's check this over here. Liquid to a vapor. I'm going to make an estimation of dP dt from a liquid to a vapor. Well, if you go from a liquid to a vapor, we know that the delta V is equal to the V vapor minus V liquid. And of course, the specific volume of a vapor is way larger than the specific volume of a liquid. So this will be larger than 0. It will increase. Actually, it will increase a lot. So the specific volume of a vapor is larger, way larger than the specific volume of a liquid. So we know that this is really large. So the difference in entropy, SV minus SL, will be large as well, but not as large as, for instance, for a solid to a vapor. So we can say that dP dt, which is of course equal to delta S over delta V, will be larger than 0. Well, from this we know that it has a positive increase. So, well, maybe let's just draw this line. It will probably look like this. So I can erase this dotted line. I don't need it anymore because I'm pretty sure the behavior of my line will be like this. Okay, so let's look from a solid to a vapor. Well, delta V volume will increase a lot as well. So going from a solid to a vapor, volume has to increase a lot. So that will be really large. And now my entropy will be really large as well, because well, going from a fixed state with everything aligned, all crystals aligned very precisely, with a very low entropy, going to the maximum state of chaos as a vapor. So this will be really large. So dP dt will be positive, and it will be steeper than the liquid to a vapor change. So let's draw this over here. It will be positive. So it will look like this. So we can erase this one. Now we've got our line over here, our saturation line. Well, and of course, then we are interested in the last one, a solid to a liquid. And from this, we know going from a solid to a liquid, well, volume doesn't change a lot. So we can say the dV is only a little larger than 0. But entropy, it really increases a lot. So delta S, or maybe the volume change will even be equal to 0 in some cases. So delta S, the entropy going from a fixed state to really more chaos will be really large. So now we know that this ratio will be really large. So dP dt will be larger than 0 and will be steepest of all of them. Steepest. Okay, well, now we can draw this line as well. And it will almost follow the line which I indicated. Now we know that this, let's take this color, that the ratio of the pressure with respect to the temperature, dP dt, at such a saturation line is equal to delta S over delta V. So now I'm going to show you how to derive the Clapeyron equation, which can be used to determine the rate of change of pressure with respect to temperature at the saturation line for the amount of enthalpy you need to add. And for that, I'm going to use the total derivative of enthalpy, which is dH is T ds minus V dP. And well, actually we know, since we're at the saturation line, that dP will drop out, since there's no difference in pressure. So this is 0. And then our equation becomes really useful, because we can write it now as ds is 1 over T dH. Okay, but over here I've got my delta S, so it's a large difference, so I need to integrate. So and of course we can write it as 1 over T H L V. Okay, and this is really useful because I can plug this in over here. So use another color. dP dt at a saturation line is equal to 1 over T HILV divided by VLV. And this is called the Clapeyron equation. And since this is dP dt, we know that this can determine the rate of change, so the enthalpy, and the specific volume can determine the rate of change of the pressure with respect to temperature in our phase diagram.
Now in the phase diagram, there are a couple of things that are quite marvelous, you might say. For example, the triple point, where apparently a substance can exist in all three phases, liquid, solid, and vapor, at the same time. And this interesting movie, it's about 5 minutes, shows you much more about it. Shows you on video what water looks like when it's in this triple point. Another interesting one is the so-called critical point, which is in a way similar. It's also a substance that exists in a phase that's neither liquid nor vapor. And there's another YouTube video that shows you in 4 minutes what that looks like. So feel free to have a look at those right now or perhaps later on. Okay, so in Wout's movie, we saw a nice derivation of the Clapeyron equation that's reproduced here. And let me bring out my pointer. So Wout explained that you can use this equation to find, for example, the slope in your phase diagram along a saturation curve if you know the enthalpy that corresponds to the phase transition, the specific volume and the temperature, but you can also do things the other way around. Suppose you would like to determine the enthalpy of vaporization, say, for a liquid to vapor phase transition. So we don't know this quantity here, but suppose we do know the temperature and we do know the specific volume, then what we could do is we could bring the system to the phase transition for a specific temperature and pressure. And then we vary the temperature and the pressure while staying on the saturation curve. So we stay on the phase transition, and in this way we can actually plot the phase diagrams ourselves. We can plot those curves, then we can compute the slope from the curve that we have just measured by basically pressure and temperature measurements. And if we know the temperature and the specific volume, then we can determine the enthalpy of vaporization, which is a very useful tool to have as a thermodynamics engineer. Now, you still have to determine this specific volume, which can be done, but it's an additional complication. So if we could find a way to get rid of that, then that would make life simpler. And we can actually do this, specifically for transitions, phase transitions to the vapor state. So liquid to vapor or solid to vapor phase changes. In those cases, we can make a couple of approximations to make things simpler. For example, this here is the difference between the specific volume of the gas state minus the specific volume of the liquid state at the phase transition in a mixed state or saturated mixture. But at low pressure, the specific volume of the vapor will be much bigger than that of the liquid. So the difference between the two is basically equal to the specific volume of the vapor state or gas state. In addition, we can treat the vapor as an ideal gas, for which we can write down the ideal gas law. So we can express the specific volume in terms of the gas constant. And hey, here's the temperature and the pressure. That's interesting now, because in that case, the Clapeyron equation becomes, with all these approximations, if we insert these into the Clapeyron equation, first of all, you will notice that this difference in specific volume is replaced by this one, which in turn is replaced by the ideal gas law. So we have this expression here, where there is no longer a specific volume present. You also notice that we have a dP here, which is actually valid at the saturation curve, at the phase transition. And we have a P here, which also corresponds to the pressure at the phase transition. And we have a dt here, and the temperature. And now let's move the P to this side of the equation and the dt to that side of the equation. Then we end up with this equation here, which is something we can perfectly integrate. We can take the integral, perform the integration, and the limits that we choose here are um, temperature 1 and temperature 2, both on the saturation curve or on the phase transition boundary, and the same thing for the pressure P1 and P2. And if we perform this integration, then we end up with this expression here. And you will notice that apart from P1, P2, T1 and T2, there's also the enthalpy, or the enthalpy of, for example, vaporization for point 1 of the curve, and here the enthalpy for point 2 on the saturation curve. Now actually we can simplify things even a bit further. So continuing with the last equation of the previous slide, we can assume that the temperature difference T2 minus T1 is small. In fact, so small that the difference between these two enthalpies, it becomes negligible. So you can treat this as the same number and take that out of the brackets. And this is the Clausius-Clapeyron equation, where well, we can use that in the same way as we would like to use the Clapeyron equation itself. But in this case, we no longer need to measure the specific volume. So life is simpler. And of course, this can also be used in the solid to vapor phase transition. In that case, we would replace the enthalpy of vaporization by the enthalpy of sublimation. And you have to remember, though, that this simplified expression comes at a cost because we have some additional requirements. This Clausius-Clapeyron equation is only valid when the pressure is not too large, such that this inequality holds. The substance, while it's in the gas phase, it needs to be satisfactorily described by the ideal gas law, and the changes in temperature and pressure along a phase boundary curve, they are supposed to be small. So let's make a short recap of both the previous class 16A and this class 16B. So we had seen the four thermodynamic energies or thermodynamic potentials, which have a full form. They also have, that's this stuff here, they have a differential form. And from these, we could derive partial derivatives that turned out to be equal to the basic thermodynamic properties, giving us new definitions of the temperature, of the entropy, and so on. In class 16b, we saw the four Maxwell relations, how you can derive these from the internal energy, from the enthalpy, from the Helmholtz energy, as well as the Gibbs energy. And we saw that how to use the Maxwell relations to derive something like, for example, the Clapeyron equation, which can be simplified to the Clausius-Clapeyron equation. Now in the next class, we will learn there's actually more to it. There's much more than the four Maxwell relations. You can do many more things than deriving only the Clapeyron equation. There are, for example, still 500 partial derivatives left unevaluated, and we will learn about a general mathematical approach to derive all these partial derivatives, or maybe not all of them. That's not what we're going to do, but we're going to be able to derive any of them, any partial derivative that we would like. We will also see that some of these partial derivatives are related to very useful properties in thermodynamics, things like specific heat capacity, expansion coefficients, or compressibility factors. And we will also see why gases sometimes cool down when they undergo adiabatic expansion, and sometimes warm up. That sounds a bit weird, right? Or a bit contradicting. Um, and this has to do with the so-called Joule-Thomson effect, and that's quantified in turn by a coefficient, the Joule-Thomson coefficient, and you will learn about that as well. Now, in the Watt reader, you may have noticed that early on in the Watt reader, there's an overview of equations, and that's all the stuff that we have derived so far. The energies, the Maxwell relations, and also some of the things that we will learn about in the next lecture, like for example this Joule-Thomson coefficient, and a form with these formulas will be provided at the exam, and the same goes for the equations on the next slide. Those will also be provided by the exam. Let me also emphasize here, of course, that the exact form of the exam is not exactly known yet, as you will fully understand. So, well, these are the important formulas. It's a slide that we have seen many times before. Many thanks once more also to Genie Stoffels for letting us use and edit her slides. And well, in the previous classes, you've seen that we like to activate your long-term memory and try to store the things that we just told about in your long-term memory. So maybe this time you can take a minute to try to answer the following questions in your mind in just one or two sentences. And these questions are, so how do the Maxwell relations come about? And what does a PT phase diagram look like? And you should try to draw a sketch by heart. And how are the Maxwell relations and the Clapeyron equation related? Okay, well, good luck with that. And we look forward to meeting you during the online session. Bye.